Hi and welcome to this video in which we will start talking about the powers of a complex number z. Powers of a complex number z. Okay, so let us start with the numeric example. Let us give a complex number z, which is 3 square root of 3 plus 3j, and we want to evaluate the eighth power of this complex number, which is as to say z raised to the eighth. This is if we use the Cartesian form, we should evaluate this as 3 times square root of 3 plus 3j times 3 square root of 3 plus 3j. All this has to be performed 8 times, and you see how cumbersome it's going to be. While if we use the exponential form, the whole thing is going to be much better, much simpler. So in the first step, let's find the exponential form of this complex number. We know the first step is to evaluate the modulus row of this complex number, and the modulus is 3 times the square root of 3 squared plus 3 squared. That is equal to the square root of, this is 9 times 3 plus 9, which is the square root of 36 and is 6. While theta is the arctangent of 3 over 3 square root of 3, we don't have to add anything because the real part of z is positive. 3 and, oh, I'm sorry. The 3 and 3, they cancel each other, so we have here the arctangent of 1 over square root of 3, which of course is pi over 6. So this complex number z can be expressed as 6 times e to j pi over 6. What if we had to evaluate the eighth power? So z raised to the eighth is the same as raising to the eighth this exponential form, and using the properties of the exponential form, what we get is 6 raised to the eighth times ej, 8 times pi over 6. Now, if we draw a diagram and we try to understand where this new complex number z to the 8 is located, we know that this is located on a circumference with the radius 6 to the 8th, while the argument of this new complex number is 8 times pi over 6. Well, this is pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5, 6, 7, 8 pi over 6. Okay, this is where z to the 8 is located. And you see how easy has been to find the power of a complex number compared with using the Cartesian form. Now, we want to evaluate the root of a complex number, root of z, okay? Root of z. What is a root of z? Well, we know that a root of a complex number is simply, for example, the nth root of z is simply the z raised to 1 over n is a power with a fraction exponent. If we use the exponential form for z, and it is reasonable, because if we found out that using the exponential form is very convenient to evaluate powers, it should be expected that this exponential form, is convenient to evaluate roots as well. So what we found here is rho times e to j theta raised to 1 over n. And this is using the usual properties for the exponential powers. For the exponential form, we found that this is rho to 1 over n e to the j theta all raised to 1 over n. Now we need to do some very simple consideration about the exponential form. And what we do here is considering that if we have the vector, if this is the vector that represent the number e to j theta, we know that this vector has a length of 1 and that the argument is simply theta. Now, what happens if we add 2 pi to the argument theta? Well, it happens nothing, because we exactly get back to the first position. So this is as to say that e to the j theta is completely the same as e raised to j theta plus k times 2 pi, where k is a relative integer. That is as to say that k could be 0, plus or minus 1, plus or minus 2, and so on. Okay, so if we substitute this new expression in this form, what we found here is that the square root, the nth root of z is equal to rho raised to 1 over n, and what is inside here is e raised to j theta plus k times 2 pi all raised to 1 over n. And again, if we use the properties of the exponential, this is equivalent to say e raised to j theta over n plus k times 2 pi over n. This is exactly what we were, this is n. This is n, of course. This is n. So keep in mind, this is the formula that allows us to evaluate the nth root of a complex number if we use the exponential form. So let's take a look at this formula. What it says is that the nth root of z is given by a modulus, has a modulus that is the nth root of rho, which is a real number, while the argument is given by theta over n plus k times 2 pi over n, where k is 0, 1, 2, up to n minus 1. In fact, for each of these k values, we got a different values of the root. And if we go up to n, as soon as we replace k with n, what we find is exactly the same value that we have obtained for k equals to 0, because e to the j theta is a periodic function. So let's try to understand this with some more example that we will see in the next video. Thank you.